Hello, my name is Keegan Wasenick, and my partner is Adam Schrader. Today, we are presenting our experimental analysis on a single point cutting tool in metal machining. To begin, our project objective is to simulate the orthogonal cutting process seen in manufacturing, such as lathe operations. To do this, we've created a simple assembly model in Abacus, which contains a cutting tool head and a material workpiece to simulate the orthogonal cutting process. The experiment is performed by varying the materials for the cutting tool, where we investigate the surface finishes and internal stresses imposed on the tool after operating on the workpiece. Here are the geometry variants. The assembly created for our simulation consists of an additively manufactured cutting tool and a workpiece of material. This slide also shows the engineering drawings of the devices with the dimensions we used. These are the materials that we have used throughout our testing and their respective properties. We have at least one specimen of each primary material type: metal, polymer, ceramic, and composite. We have selectively chosen this to study the behavior of each one, hoping to draw conclusions about the advantages of one versus another during comparison. Here, we begin summarizing the mechanical relationships for our materials, beginning with 88% alumina. For processing, alumina undergoes a Bayer process, which includes a solution wash and heat treatment. This results in a hexagonal crystal lattice structure that gives alumina chemical and physical stability with nice strength and hardness ratings. Alumina is favored for applications such as kiln brick construction and electrical insulation. Moving on to high density polyethylene, the processing is a simple polymerization, which results in very long chains of bonded ethylene. This results in a plastic polymer with very high ductility, low tensile strength, and low yield strength, and polyethylene is one of the most common thermoplastics used in 3D printing. For structural steel, an oxygen converter process transforms carbon-rich iron to steel by heat treating the iron and blowing oxygen across the top of it. This forms a steel with the BCC ferritic structure. Structural steel has a favorable durability and flexibility for the construction industry, with good hardness and strength properties, which causes it to also perform well in machining. And lastly, tungsten is ultimately formed by a chemical reaction between wolframite and graphite. The resulting structure is a hexagonal structure with a grid of tungsten and carbon. Tungsten carbide is one of the strongest materials available, rivaling diamond. It has a very high hardness, strength, and wear resistance. It is a good material in the machining industry because it maintains its shape when working, and due to its mechanical properties, it is one of the most sought after cutting and machining materials. Each of our materials can be additively manufactured. Only polyethylene is simulated in this experiment, but each process to additively manufacture or 3D print the material is listed here. Polyethylene is used in fusion deposition modeling, while the rest of the materials can be used in powder bed fusion. Powder bed fusion commonly uses a laser beam as a heat source, which selectively melts powder pellet-like materials. Any excess powder not melted into the geometry can be used as a support structure. Fusion deposition modeling uses a heat bed and extruder. The extruder melts thermoplastic filament onto a heat bed, and the heat is used to activate adhesive properties, and the extruder is programmed to then create an uploaded geometry. The additive manufacturing process is simulated on ANSYS using the transient thermal tool. This process would be standard for parts manufactured through fusion deposition modeling. A convection condition is used to simulate the heat bed, and a heat flow condition is used to show the direction that this convection travels through each layer construction. The element birth depth tools are then used to indicate the start and finish of each layer construction, and the mesh we used is also listed here. These are the corresponding results from the additive manufacturing process for the printed polyethylene. The temperature gradient shows the direction of heat flow, where the bottom of it is the hottest as it was the last layer to be formed. The temperature and deformation contours are near symmetrical as they follow similar time-based behavior. The engineering stress and strain experienced magnitudes at the top, as this is the boundary condition for the tool used throughout the project, and this area is not allowed to displace, so stress concentrations um, occur in this area. For fun, we have gone ahead and simulated the remaining cutting tool materials to see the differences in behavior, but for the sake of time, I will just show you the images for now. So here are the alumina 88% results, here are the tungsten carbide results, and here are the structural steel results. For our boundary conditions, the bottom section of our base is encastered, leaving the top partitioned portion free to deform. The top of the tool is held fixed at the top face and moves 80 millimeters in 1 second. Note, this does mean it experiences an instantaneous acceleration, which prevented us from modeling faster cut speeds. Here are the mesh sizes we use in Abacus. It should be noted that the polyethylene was the primary material modeled with plastic deformation properties to simulate its polymer properties and the effectiveness of additive manufacturing. To adequately prepare our Abacus simulations, we wanted to test the behavior of the assembly. Abacus has the ability to accurately simulate the physical system results, which will be seen shortly. To do this, Johnson-Cook damage evolution data has to be enabled and applied. This will allow the elements to degrade under multiple dimensions of stress. This is coupled with element deletion so that when the degradation occurs and elements get stretched to the point of nodal detachment, the elements are deleted, or else they would end up looking like the image below.
This is the starting orientation for all of our simulations. The tool moves from right to left through the entire length of the workpiece. Before we get to the simulation results, we need to address an interesting behavior that we noticed, as it's one of the driving factors in our results. We said that one of our objectives was to compare the surface finish left by the tool, and in our preliminary simulations, we were getting some incredibly rough surface finishes at the beginning of the process, but smoother cuts by the end. It looks like the blade isn't cutting low enough in some spots, but we're keeping the top of that blade at a fixed height, so we were wondering why some of these elements were remaining uncut. We realized that the entire blade tends to oscillate left and right, which results in the cutting edge moving vertically relative to the workpiece. The scale factor here is exaggerated, but you can clearly see how the height of the cutting edge varies as the tool moves through the aluminum block. We can explain this behavior by thinking of the tool like a spring. It initially starts against the workpiece, and as the top of the tool moves forward, the bottom of the tool is pressed against the aluminum, blocking the tool's path. Before the aluminum yields, the tool ends up stretching back slightly, and once the aluminum fails, the tool tip is released and immediately springs forward. With the tool stretched back, the cutting edge is lower than it started. Once it snaps forward, that cutting edge is higher. This results in the uneven removal of material, and looking at the contact force between the tool and the workpiece further solidified these findings. There's a clear oscillating pattern. As the tool hits the aluminum, the force increases until that aluminum yields, in which case it rapidly drops, and this process repeats through the entire process. To better understand the impact of these oscillations, we ran a simulation with the tool as a rigid body to see what the ideal cut would look like. Some of the first elements do get a little mangled, but the main takeaways here are that it doesn't dig into the first cut at all, and the cut leaves a completely even surface with a uniform strain distribution, which exists almost entirely in the top row of elements. Here's an animation for the steel tool's cut. It appears to have a very nice and uniform peel. We can see 3 distinct layers at the start of the cut, but afterwards the cut height is pretty uniform. However, we can see very clear hot spots in the strain curve that spread well beyond the top layer of elements. While the stresses in the aluminum did vary slightly, only by a couple of percentage points, we know it will deform the aluminum. We're just concerned with the stresses in our tool. As our tools are fixed at the top, there's an obvious stress concentration there. However, in actual use, the tool is held by a tool holder. It would not have this same concentration. Therefore, we're only focusing on the stresses near the cutting edge of the tool. For steel, these stresses range from around 150 to 350 megapascals. Seeing as the yield strength of mild steel is only 250 megapascals, this tool would surely plastically deform and not be viable for this machining operation. Here's an animation of the alumina tool's cut. It also appears to be a pretty continuous ribbon. At the first cut, we can see a distinct row missing, and then another row that's missing or distorted a few more elements down the way, a clear indication of an oscillation. This is also seen in the profile of the entire cut, but becomes very smooth with minor strain concentrations, and looks similar to the strain profile seen in the rigid body cut. Stresses at the tooltip are approximately 160 to 270 megapascals. High purity alumina has a flexural strength of 260 to 360 megapascals. So while this might technically be able to cut a very soft metal like our aluminum alloy, it is already at or below a safety factor of 1. It would not be an appropriate material to use for our tool. Here's an animation of the tungsten carbide tool. Pay close attention to the beginning as the cut material initially flies off before settling into a uniform ribbon, which still has some splits at the tip. Similar to the alumina, we can see a single row of elements missing at the first cut, and then another dip back down, indicating a quick oscillation occurred. We can also see a few elements a little further down that were seemingly pulled out of the corners by the cutting edge. The strain profile eventually does become quite uniform and similar to the rigid body, but notably has a few more hot spots than the alumina did. Stress at the cutting edge is 270 to 600 megapascals, while tungsten carbide has an absurd flexural strength of around 1800 megapascals. This gives it a minimum safety factor of 3, and it's the only material we tested to convincingly withstand its cutting force. Unfortunately, polyethylene didn't quite make the cut. To be clear, this is 1-to-1 scale, the same as all the other animations shown previously. There's no cross section of the workpiece to analyze, and we don't need to analyze the internal stresses to clearly see that this would never result in a usable tool for metal machining. To sum up our findings, the only material deemed usable for our machining operation was the tungsten carbide. It gave a smooth cut, almost on par with the rigid body tool, while having a nice factor of safety of at least 3. If this assembly were manufactured and put into service, a number of problems may arise. The boundary conditions we used led to significant movement of our cutting edge. Our machining process occurred at a relatively slow speed of 80 millimeters per second, and in the real world, massive amounts of heat can be generated during machining, which we were ultimately unable to accurately model and thus neglected to include them in our final simulations. Any or all of these factors may hinder the viability of our results for real world comparison. Thank you. We will now open the floor for questions.